So what I was going to do in this, well, in logic we have, I would say, two big traditions, the syntactical one and the semantical one. And, the logicians in the syntactical tradition were trying to found logic as a system of proofs, or which will generate all logically valid formulas and logical implications. And one of the first really comprehensive proof systems were axiomatization by Frege in the second half of the 19th century. And here is his axiomatization reduced to the first order logic, because of course he was dealing with higher order logics also. So he had these 8 axioms and 2 rules of inference, modus ponens and generalization. But if you ever had to do something with such axiomatic system, then you'll find that it's really very hard to handle it. For example, if you want to prove that if A, then A is a valid formula, the trivial one, you have to have some time to work it out that it is derivable from this proposition. So to handle it easier, you should develop some derived rules, which will make things easier. And the first such derived rules, which is almost always the first one to be introduced, and it was also introduced by Frege and others, is the so-called theorem of deduction. This is this one in the left up corner. So if you assume A and if you succeed to derive B from this assumption, then you can derive if A then B without this assumption. So this is the so-called theorem of deduction, or it is also called introduction of conditional. And then you see that you can make such rules, derived rules for negation and for contradiction and for universal quantifier. They are all here. And I would like you to note is that some of these rules are global and some are local. And I would say, what do I mean by that? So this introduction of conditional, this theorem of deduction, is a global rule. Why I call it a global rule? Because to deduce if A then B, it's not enough to look at the formula before, just at B. You have to look at the whole derivation to see what are the assumptions of this derivation of B, and then you discard this assumption. So you have to have a global view of the whole derivation to apply this rule. And for example, modus ponens, which is also called elimination of conditional in this context, is a local rule. To conclude B, you just have to look at the previous formulas, A and if A then B, and you don't have to look at the whole derivation. And this will be interesting further in the presentation. Now the people recognized, especially Gensen recognized, that these derived rules are actually very symmetric. You have one for each connective, you have one rule for introduction of the connective, one rule for the elimination of the connective. And so you have this system of introductions and eliminations. And he realized that if you just use these rules and not the original axiomatic, you have the equivalent system. And this is his system of natural deduction, of course. So Gensen realized that his system of natural deduction is equivalent to these axiomatic systems, let's say Frege and others, which we developed before. So I will skip these proofs of the equivalence and just note Of course, when you introduce other connectives, conjunction, disjunction, and existential quantifier, you get the complete natural deduction system of Gensen. So it's Gensen's natural deductions. Now, Gensen made a second move. It's just a little bit of history. I'll skip this. That you can present this system of natural deduction in sequent format. So if you look at the left upper rule, which says, well, this is just the introduction of conjunction. You know, if you have a derivation of A from gamma 1 and derivation of B from gamma 2, then you have a derivation of A and B from gamma 1 and gamma 2. So this is just nothing new. This is just another way to describe this introduction of conjunction. And similarly for elimination of conjunction. If you have a derivation of A and B from gamma, then you have derivation of A from gamma. This is just elimination. And so if you look at the first left column and the second column, which is in brackets, these two columns are really a natural deduction system written in another format, in sequent format. So there's nothing new here. But what Gensen realized is that you can, instead of these elimination rules, you can use introduction into antecedents. So you have these equivalences. So to eliminate conjunction is equivalent to introduce conjunction into antecedent of the sequent. And he proved these equivalences. It is easy to prove them by using the cut rule. So, so he get in this way this sequent system for logic, and I will, what's going on now? I'll skip the proof of these equivalences, so it is just to see, it's quite easy to prove that. On 2 slides you have all the proofs. And then Gensen also realized that he can use empty consequent instead of contradiction, so it's simplified the notation. And also now he has in consequent he could have a singleton or empty set of consequence. And the further move was really inspirational, that he realized that if he allow for multiple sequence, more formulas in the sequence, then he have a very nice and symmetric presentation of classical system. As you see, then it is very easy to prove, let's say, this crucial rule for double negation just by moving the formula from left to right, but you have to but you need multiple on the right side. So that's the, in a sense, the tour from axiomatic systems via natural deductions to sequence systems. It was mainly done this last part by the Gensen, but there are also other people, Jaschkowski, and so it's not only Gensen, but I'm not going deeply into the history. And now we have also this semantic tradition, which starts from the meaning of classical meaning of the logical constants. You just, so we are not devising a proof system for all the logically related formulas and applications, but you just analyze formulas according to their meaning. So let's give some examples. So you ask the question, what does it mean that if A and B is true? And then your meaning of this is, well, it means that A is false or B is true. You know, this is the first rule, upper left. And the second one below that, what does it mean that if A then B is false? It just means that A is true and B is false. So this is the second rule, and you make some analysis for all these connectives and quantifiers, and you have the crucial steps for analysis of the formulas. And yeah, now I this is in the column on the left side, and on the right side, I'm just giving you the same stuff, completely the same. There is nothing new, but just written in the different way. I call it quote, Gensen quote notation format. So we have this negated turnstile, and if the formula is on the left side, it means it means that it is true, and if it's on the right side, it means that it is false. So this rule, what does it mean that if A then B is true, is just what does it mean that if A then B is on the left side? And then the answer is, well, it means that A is false or B is true, which means the truth. It means that, well, either A is on the right side or B is on the left side. So you have completely the same. There is nothing different, just another notation. And then when you analyze if something implies something or if something is logically valid, as you know, with Beth Tableaus, this is all well known, of course. Then you start with the formula, and if you want to prove that it is logically valid or logically true, you ask the question of what should be that it would be false? Is it possible to make it false? And then if you cannot do that, then it must be true. So you make this analysis according to these rules. Or for implications, of course, that formula implies another formula, means what should be the situation in which the first one will be true and the second one false. And here is one example. I don't know how to turn this, but you know, it's just turn your head. Well, what does it mean that this formula implies this formula? It means that I must make this one true and this one false, and then analyze. This will be true if there is an object A such that this, and so on and so on. And when I make this analysis, I finally realize that I should make some atomic formula true and false, which is not possible. And in another path, you can also, then all paths are closed in this way, so it's not possible to make that, so it must be this implication. But my point here is this is the well-known Beth Tableaus method. But what is interesting that if you put it in this other format, just the same but just different notation, you see that what you get is a proof in Gensen multiple system. If you read it upside down, then you see it is just that. So you can say that Gensen sequence system, multiple sequence system, is just nothing more than Beth Tableaus. So you can see it as Beth Tableaus. And it was realized, I would say, almost Beth didn't use these trees, but Tableaus, which is a little bit different. So it was not clear immediately that it is the same. But if you write this Tableaus in the tree format, then you immediately see that it is completely the same. And what is interesting that you immediately realize that cut is not needed because there is no cut in Beth Tableaus. So Gensen system without cut is equivalent to Gensen system with cut. And that was realized, I would say, almost immediately after the introduction of Beth Tableaus, but it's the first time I've seen in published. I think, well, as far as I know, it was in this Melvin Fitting's book on proof systems in model and intuitionistic logic. This is this book about Tableau systems for model logic for intuitionistic logic. That was the first of the books which deals with that. And then there you have explicitly written that just turning upside down this Beth Tableaus, you get a Gensen system.
Was that proof?
Sorry?
It was just like a hint, or?
Well, it was, but the proof is almost nothing. You just, I mean, this is the proof. If you see, if you Beth Tableaus closed, then you just read it in another way. You see that these are just Gensen's rules. So there is almost nothing to prove. Yeah. So you say, yes, it is proved, but the proof is trivial. And now to Kneale's system of, so Kneale wanted in his history of what was history of formal logic or something like that was the book called William and Martha Kneale, this classic on history of logic. There is a chapter on natural deduction, and in this chapter he introduced multiple natural deduction, which means natural deduction system with multiple consequences. So it was, his idea was to generalize Gentzen singular system of natural deductions in the syntactic tradition, but his main motivation was really simplification of the Gentzen system in the way that he didn't want to have these global rules. He wanted to have all his rules to be local. So when you're applying a rule in a natural deduction system, so you don't have to look at the whole derivation, just what are the preceding formulas, like in modus ponens and not like in introduction of conditional. And he realized that if he allows for the multiple consequences, that he can do that. And that was the main idea, you know. So, for example, he's just let me see what I have further. So, so what was my idea in dealing with this Kneale system, which was devised in this syntactic tradition? I would like to show, and I showed in this paper, that we can view Kneale system also as a notational variant of Beth Tableaus. And how did I do that? Well, I started with the Gentzen multiple system, which is notational variant of Beth Tableaus, as we have already seen. And then I realized that every application of Gentzen rule, let's say the first one, you see, if I could derive A from gamma 1, A or delta 1 from gamma 1, and B or delta 2 from gamma 2, then I can derive A and B from gamma 1 and gamma 2. And it really corresponds to this natural deduction proof on the right side, as you easily see. But also these introductions into antecedents, let's say, which was this introduction was really a global rule. If you remember the rule for disjunction, if you know that for Gentzen system, then you have A or B, and then if from A I can conclude C, and if from B I can conclude C, then I can conclude C and discard and B. But if he takes just that from A or B, he can conclude A or B, just a multiple consequence, then this is just a local rule which is described and corresponds to the Gentzen rule on the left side. And the most complicated perhaps is conditional. When you have modus ponens, then you have this correspondence. This sequence rule corresponds to this application of the Kneale's rule in his developments. He calls these derivations, which are not trees with the root, but more general, I would say, directed graphs without cycles, which are actually trees without roots. Then you have this correspondence, and this is the most interesting. So you see, introduction of conditional was global rule, but now you have these two rules, this multiple one from nothing, so it's axiomatic that A or if A then B, and from B you can deduce if A then B, and these two rules are equivalent to introduction of conditional, which was global rule. So he managed to have this local rule, and for negation you have. Sorry?
What about subformula property?
I think I didn't thought about that.
Okay,
But
okay, we can discuss.
Yes, we can discuss. So he, and of course we have also the correspondences for quantifiers, and well, using this inductive definition of this correspondence, I proved that, as a matter of fact, whenever you have this Gensen proof, you can just write it in the another format and get these Niels rules and vice versa. So Niels developments are just a notational variant of Gensen's multiple derivations, and because these are notational variant of Beth's tableau, so Niels rules are also a notational variant of Beth tableaus. But let me tell something about this. The idea of Neil that he could get rid of global rules. Well, he succeeded on the propositional level. There is no global rules for through functional connectives, but you have global rules, of course, for universal quantification introduction in the consequent, and of course for existential introduction in antecedents, because to conclude from FA to for every XF, you have to look up on the derivation to see that in the assumptions for this derivation there is no A in the formulas which are assumed. So it is actually a global rule. So he succeeded to eliminate global rules in propositional part, but not in.
He was missing contraction.
Sorry?
He was missing contraction.
Yes, I'm just going to say this. So this is a Neil system, as you see. So all these rules which don't have star are local, but we have global rules for universal quantification and for universal in these two cases. And of course, he didn't realize that he need also these rules, as Marta said, contraction. Schosmet and Smiley showed in the 80s, I think it was, that his system was not complete, because he was there was no the developments just graph without cycles. So his proofs were graphs without cycles. But Schosmet and Smiley realized that you need to have some cycles. You need to have cycles of this form. For example, if you go from you have A, and then that you can something like this, you know, when the same formula is and it looks trivial and perhaps you will think you don't need it, but actually you need it. Here's, I think, one example. I think this is an example for Schosmet and Smiley. You know, this distribution of disjunction through the conjunction cannot be proved without this contraction rule. So you have, I'm instead of Schosmet and Smiley who are allowing for these special cycles. I mean, it's much more better just, and this is equivalent, to introduce the rules that when you have one assumption, and if this assumption is already in the proof, you can discard this assumption. So you don't have to repeat assumptions in a sense, and same for the conclusions. This is equivalent to this simple cycles which should be allowed by. And so, of course, and this is also not a local rule, because when you want to discard an assumption, you have to look to the whole derivation if there is another such assumption somewhere. So it's not local. So we have 1, 2, 3, 4 non-global rules. So we could say, well, he succeeded to eliminate global rules from propositional logic, but not really eliminate them, but to move the globality from the connectives to the structure of the proofs, you know. Let's say allowing some cycles or allowing discarding the assumptions if they are repeating. So to move the globality to the structural level in a sense. So, but that's also interesting. So there is no simplification he hopes for. Yeah. But this is just the side remark. Well, what I wanted to prove is this, what I said, that each Gensen's multiple sequence deduction generates this, I call them W Niels deduction. These W are just these contractions, you know. And because of that, every W Niels deductions are just another format of the Gensen multiple sequence deductions. And we already know that Gensen's multiple sequence deductions are just another format of Beth's deductions. So the final conclusion that these Niel deductions are just another format of Beth deductions. And I'm, as you already noticed, a big fan of Beth's approach to, to logic. And I would say, so that was in the, my motivation for this. And I would say the best kind of foundation of at least classical logic is to start with Beth's analysis of the meaning of constants. He's testing according to these meanings, and which gives you Beth Tableaus. And then all these other systems, we know natural deduction, sequence systems could be seen as just a notational variant of this crucially important Beth Tableau method. Well, thank you.